Hello, everyone. In this video, I'm going to talk about some applications of Newton's second law in the case when there is no friction. And in chapter 6, we'll actually look at cases where we include friction. But we can wait on that. In fact, the activities in the week 4 lab all are frictionless. There is no friction involved. So you can see I've got Newton's second law, frictionless applications. And this is what I kind of lectured over in the class, maybe a little more condensed version of that. But also you will see the situations that are in the week 4 lab activity. So first of all, let's talk about some of the forces that we see near the Earth. Let's say you just have a block that is sitting, or maybe a book sitting on a table or on the ground. Again, I apologize, the drawing, I have a hard time drawing straight lines with this tablet. But imagine a book or a block sitting on the table. What forces are acting on it? And this is the first question we have to answer when we do Newton's second law problems. Now, there's a force due to gravity, which we call the weight force. So any object with a mass has weight. And if we think of Newton's second law, right, the force has to equal mass times acceleration. Well, the force due to gravity will accelerate objects downward at g, 9.8 meters per second squared. So the weight force is equal to mg. So this mass has a weight force pulling straight down equal to mg. All right, and so that's anytime you're near the Earth, you're going to have this weight force pulling on the object. And notice the weight is bigger for a larger mass. So for example, in fact, if you took an object like a book to the moon, it would have the same mass, but it would have a different weight because the g, the gravitational acceleration on the moon, is smaller than on the Earth. But for now, we're near the Earth, and so our g is 9.8. Now, the table is stopping the object from being in free fall. And the only way that it can do that is to apply a force that kind of cancels out the weight force. And so the table is actually pushing up on the book. If the table broke or the table was not there, that force would disappear and our object would accelerate downward at g due to the weight force. We call this force from the surface of the table the normal force. And I'll usually label this as F sub n. The reason it's called the normal force, that's a mathematical term. The normal force is always perpendicular to the surface. So it's always perpendicular to the surface that the table is on, or that the object is on. Could be the ground, it could be the table, it could be any other surface. And so let's go ahead now and look at the situation. What if I tilted the table a little bit? If I tilt the table, well, now we are kind of on a ramp situation, right? And so this is the table, but let's just draw it as a ramp here. So I've tilted the angle, the table so that there's a slope of theta. Now the book is like this. And in this case, it's of course going to slide down the table or the ramp if there is no friction. But we still have our weight force, right? And now the normal force is going like this. It's always perpendicular to the surface, right? So it's perpendicular to this direction. Now, when I do problems like this with the ramp, I'm going to make a change in how I do it. And the reason I make this change is I know one thing. The acceleration is going to be down the ramp. It's parallel to the ramp. So it would be nice if I could choose a coordinate system where one of the components of the acceleration is 0. And I can do that just by, for example, choosing my x-axis to be up the ramp, which would then make my y-axis perpendicular, right? So my y-axis is going to go this way. And again, right, what this does is make my ax equal to my acceleration because it is down the ramp, and my AY equal to 0. And this will simplify our situation, because if I want to know or apply Newton's second law to this, what I always do is add up the X components of the force and set them equal to MAX, and then add up the Y components of the force and set them equal to MAY. So this is always the case, but I can choose whatever coordinate system is most convenient for the problem I'm doing. And so now I need to get the components. Well, the normal force is easy, right? It only has a Y component. But let's look at the components of the weight. So I need a component that is perpendicular to the weight or the surface, and one that is parallel. So I like to draw it like this. I could have drawn the X component over here, but I'm always going to choose it here, or I mean, wherever you draw the components is fine. But I need to do a little bit of geometry to realize that my angle theta here is equal to the slope of the ramp. All right, so the angle right here is equal to the slope of the ramp. And you can see that just because the two triangles that I've drawn, the ramp and the vector components, are similar triangles. Now, since this is the opposite side, the X component is going to be mg sine theta. And the Y component is the adjacent side to this angle, so it's mg cosine theta. All right, add up the X components, there's only one, negative mg sine theta. If I say the negative direction is down the ramp, well, that's equal to ma, right? The X component of acceleration is the full acceleration. Here we see a common thing that happens. The masses cancel. When you're dealing with gravity, gravitational forces, weight forces, they will often cancel. And the acceleration should not depend on the mass. It is just negative g sine theta down the ramp. We can check this, right? If the angle were 0, we'd have a flat surface. The sine of 0 is 0, and there is no acceleration, which makes sense because, right, you're flat. There's no slope to the ramp. We can also add up the forces in the Y direction. Now, there are only two forces here, our normal force going in the positive Y, and then our mg cosine theta going in the negative Y. But those will add up to 0. As we talked about, we chose our Y-axis, so the acceleration in that direction is 0. So what we can do with this is we can solve for the normal force. Right, it's equal to mg cosine theta. And so often what happens if you know the acceleration, for example, if it's 0, you can solve for an unknown force. If you don't know the acceleration, hopefully you have forces like we did for the X direction here to solve for the acceleration. And of course, you could use that acceleration now to figure out, for example, things like how much time does it take for the block to go down the ramp? You know, how fast is it going? What is its speed at the bottom of the ramp? And you would just do that using the kinematic equations once you know the acceleration. Okay, so this is the trick for ramp type problems to, tilt your coordinate system. And you will see this in one of the problems, the ramp problem. They actually show the coordinate system below the problem. I forget, I think maybe it's problem 3, but that's what they do in that problem. Now, in that problem, there's a problem on the homework, which has a rope, right? And the rope goes like this, and it attaches to the wall up here. Now, that rope is going to make the acceleration be 0 because there's a new force, right? There's a tension force from the rope that holds the block. So any situation where we have a rope, we say there's a tension force acting from the rope on the block, right? We call that T for tension. And in this case, that would make this what we call a static problem. The full acceleration is 0. All the forces should be balanced. But what would change in that situation? There's only one thing would change, right? You would add this tension force into your X components, because it's pulling up the ramp. And you would set your acceleration in the x direction to 0 because you know it's not sliding anymore. Then you could solve for the tension. So hopefully that will also help with one of the homework problems. So the next thing I want to do is look at tension in a couple of other situations where the objects are accelerating. And this often happens if we have two objects connected together by a rope. So let's look at this situation, which is a situation that occurs in the week 4 lab simulation activity. Let's say we have two masses, M1 and M2, and they're connected by this rope or string over a frictionless pulley, right? And so what will happen, of course, without friction is that the masses will start to accelerate to the right, or kind of the pulley will start going clockwise, and you'll get an acceleration of the two masses. A question that you will encounter in the week 4 lab activity is, what is that acceleration? You will measure it and you'll be asked to compare it to Newton's second law. So how do we get the acceleration from Newton's second law here? Well, just like the ramp problem, what we have to do is we have to first of all draw all of the forces on each mass. Now for M1, we have a weight equal to M1G, and there is a tension from this rope pulling upward. Right? And one of the things that I can do is I can just add up the forces on each mass by itself. But let's do that in a second. We're going to look at the forces on M2 first. So M2 has a tension force, right? It's moving to the right, or pulling to the right. The two tension forces are equal and opposite to one another. They are actually an action-reaction pair. And so they have the same magnitude, but they are really opposite in direction. In fact, this problem is really just a one-dimensional problem, right? Because it's kind of like you took the x-axis and wrapped it around the pulley. So this would be my positive x direction, and this would be my negative x. So any force making the pulley go clockwise is a positive force. Any force making it go counterclockwise would be a negative force. There are a couple other forces on M2, right? There's its weight and the normal force from the table. However, those forces are y component forces. They do not affect the motion in the x direction. So what I can do is I can go ahead and add up all of the forces on both masses in the x direction, because I know that the acceleration in the y is 0. And I just remember that my x direction sort of wraps around the pulley. So I have this tension minus this tension, or yeah, since this one's negative, since it's going in the negative direction. And then I have plus M1G, right? That's the sum of my forces. So one thing to notice here, the tensions just cancel each other out. The tension, really all it does is hold the blocks together. Okay, and so they cancel out. So the sum of my forces is just M1G. Makes sense, because the only force that's really causing the blocks to accelerate is the weight of block 1. Now this has to equal, though, since I've added up the forces on both masses, has to equal the total mass, M1 plus M2 times the acceleration. So now I can easily get a formula for my acceleration. It is M1 plus M2, or sorry, M1G, the force, divided by M1 plus M2, which is the total mass. Okay, and so now I've got my acceleration. This is what we would compare to in the week 4 lab activity, right? You measure your acceleration and then see if the formula actually matches that acceleration. But again, this is how I just apply Newton's second law. I draw a diagram containing all the forces, make sure I have all of them. I add up the forces in the x and y directions, set them equal to max, may, and solve for A, or solve for any unknown force. Now, I didn't use the y direction here because I know that the normal force is just going to equal m2g. Now, one other question sometimes occurs. What actually is the value of the tension? Well, once I know the acceleration, I can now go and look at a block individually, right? I could look at block 1 and say, okay, what are the sum of the forces on block 1? Well, they are equal to the negative tension, right, plus m1g, and that has to equal m1a. Notice I only set the forces that are acting on m1 equal to m1's mass times the acceleration. So I can look at it in two ways. I can look at it as a complete system. M1 and M2 are just, two parts of a whole system. They're stuck together by the rope. Or I can actually look at each mass individually. But what I could do here is now I could solve for t using the acceleration of the system we found. I could also do the same thing on mass 2. If I add up the forces on mass 2, there's only one pulling in the x direction, the tension, and that should equal m2a. So again, I can just apply Newton's second law to any mass I want. I just have to add up only the forces acting on that particular object and set it equal to that object's mass times acceleration. Okay, one last situation for right now. Let's look at the case when the table is not there. So what I mean by that is we have just a pulley. This is another situation shown in the week 4 lab activity. So I've got both masses just hanging on opposite sides of a pulley. Now, if the masses were equal, there would be zero acceleration, right? Because m2g is pulling this way, kind of in my negative x direction, and m1g is pulling the other way in my positive x direction. Now, there are tension forces in the rope. But again, all those tension forces will do is hold things together. So let's add up the forces. Not surprisingly, if I add up the whole system, the forces on the whole system, we'll say all forces, I get m1g pulling to the right minus m2g pulling to the left, right? Now, since I'm, again, adding up the forces on both masses, I set that equal to m1 plus m2 times a. So again, I can solve for a. And I will notice I can actually factor out a g here and write m1 minus m2g over m1 plus m2. So in the week 4 lab activity, what they do is they have you adjust the masses. So first of all, that m1 minus m2 is the same, right? The difference in the masses is the same, which means that the total force pulling is the same. It doesn't change. You might have more mass, but the force doesn't change. However, if you add more mass either to m1 or m2, you get a larger inertia, a larger mass, which will drive the acceleration down, right? And so it shows if you apply the same force to a bigger mass, the acceleration is less. Again, in this situation, if you wanted, you could solve for the tension just by applying Newton's second law to one mass individually. For example, m1, I would have a negative tension force, right? I'd have negative T right here, plus m1g equals only m1a. And I could again solve for the tension because I know what the acceleration is. Okay. So there are a bunch of different situations that we can encounter. I think the only type of situations you will see on the exam, however, are situations similar to the homework problems. And there are a couple ramp problems. So you could expect to see a ramp situation on the exam. These pulley problems will not be on exam 1. They may be on the second exam. But I'm going to cut it off at the homework problems that we've given up through chapter 5. After the exam, we'll come back and do more of these. We'll add friction and look at several other situations involving Newton's second law. Again, though, right, we're always just adding up the forces and setting them equal to mass times acceleration. That's really the main principle here.